Hello, my name is Macy Watley, and this is my last lab, the physics of an extreme rope swing. The problem: we're investigating the physics behind the world's largest rope swing. We're drawing connections between the jumper's motion and the motion of a pendulum. We're investigating how the rope behaves in terms of the momentum principle, the energy principle, and the force of tension. The main results: we are able to predict the motion of the jumper using the energy principle and the momentum principle, and we can model this in VPython. Initial conditions. The explanation video can be found at this link. The initial conditions were given in that. The length of the rope is 45.72 meters. The initial drop is 39.62 meters. At the bottom, the very bottom when they're swinging, they're 10 feet from the ground. The mass of a jumper is approximately 70 kilograms. That's just the average mass of a human, looking at the people who are in the video. And at the bottom of the swing, the angle is 90 degrees. Velocity, using the energy principle. The change in energy is equal to work. So we have K initial plus U initial equals K final plus U final. 1/2 mvf squared equals mgh. We know this because U goes to 0, and in the end, so does kf. So 1/2 times 70 times vf squared equals 70 times 9.8 times 39.6. That's all using the height, gravity, and the different constants. So vf squared, or the final velocity, is equal to 27.9 meters per second. That's 66.43 miles per hour. So this rope swing is definitely a thrill. The force of tension. At the bottom of the rope, the angle is 90 degrees. We know F net perpendicular plus F net parallel F perpendicular plus F parallel is equal to F net. The F parallel is 0 because it's at the very bottom and the degree is 90. And so F perp is equal to magnitude of momentum times magnitude of velocity over R times n hat. So we do all the math there, and we find the tension, which T minus mg equals mv squared over R. So the tension is equal to 1875 newtons. Speed and tension at an angle. So now we're going to look at this from a 30-degree angle. The change in kinetic plus change in potential is equal to 0. Kf plus Uf equals Ki plus Ui. That's just decomposing that into parts. So we have 1/2 mvf squared plus mghf equals mghi. So the heights are changing there. So you're going to have different potentials based on the height, and that's what we're doing there. And we also know that the initial is going to be 0. The final velocity we get solving that is 24.5 meters per second. So the height is equal to L minus L cosine theta, which gets to be 6.125 meters. We use this from starting at 10 feet, which is 3.048 meters. The height in an angle is 9.173 meters. So we can find force tension to be 1,511.6 newtons. The stretch at the bottom and angle. So at the bottom, force tension is Ks times S. So Ks is 29,000, and the force tension is 1875. So we get S to be 0.0647 meters. At a 30-degree angle, we use the same formula, and we get 0.0521 meters. So here, now we're going to take what we just did in physics in person on paper to go to a Python model. So I'm using, I used the skeleton of an old lab we did using a spring, because this rope is very similar to a spring with just a very different Ks. So you can see the initial conditions here. Gravity, the mass 70, the L naught 45.72, the Ks 29,000. I chose delta T to be very small so that it'll update as it's going. The rest are just getting the visuals to be added in. Down here you see the ball's momentum is equal to 0 because the initial velocity is 0. So here's the calculations. Throughout this, you can see, calculating L, the change of where the jumper is versus how long the rope is, things like that. The force of the spring we have here, the updating the position using the momentum principle. Down here you can see F net tangent and F net perpendicular, and all this is going to be updating, every smaller than a second. So we're going to get very accurate results. Here's the last little bit of calculations. Again, updating the position, looking at the spring axis, and updating that so we can have it moving the way it needs to be moving and modeling it correctly. So now I'm going to show you my model. So this is what the module looks like when it's run. And the arrows are the force tension and the momentum. And the F net perpendicular and F net parallel also being measured. And so you can see that this is the motion of the pendulum just as much as it is the motion of the jumper, which is exactly what we want to see. I've already run it once, so you can see it spits out the final velocity here, the final position, the final net force, the force tension, the F net perpendicular, and F net tangent, which is all exactly what we calculated it to be by paper. So that's really great to see that the results are being the same. So in conclusion, you can see that the model is successful at predicting the motion of a jumper using physics principles like the momentum and the energy conservation principles. So it's really cool to see that you can take a really cool rope swing and use physics to figure out how it works. Thank you for listening, and I hope you have a great day.